As Jing said, I'm going to talk about the EFT perspective on an important question at the interface of particle physics and cosmology, namely, was there an electroweak phase transition? And before I go there, I want to say a little bit more about myself. Since I have multiple institutions listed next to my name, I thought I'd say something about that. So as Jing said, I have positions at the TOLI Institute in Shanghai and ACFI at UMass Amherst. And so in the Shanghai group, we're focusing on the topics I'll talk about today: early universe, quantum field theory, phase transition, and collider phenomenology related to it. UMass, the focus is more on fundamental symmetries and electroweak precision tests. And so this is kind of a global effort now that I'm involved in. It involves of order 18 researchers. And one of the key points for myself is I now see myself as having a role in this community of fostering scientific connections across the globe, in particular between people in the USA and the West and in China. And I've been inspired by actually my PhD advisor, Sam Treman, who worked very closely with T.D. Lee on the Cuspia program that brought early career Chinese scientists to the US to build those scientific connections. So whatever is going on globally in the world, politically or with coronavirus, my philosophy is that science comes first. And so that's motivation for this kind of odd configuration. And I did want to focus on science first. So I'll be talking about this topic here in the red box, but I want to also introduce you a little bit more to the T.D. Lee Institute, since this may be new for you. It's founded in 2016 in honor of the great legacy of T.D. Lee, who was from Shanghai. And its mission includes bringing the world and Chinese science together, helping early career scientists develop their careers and developing new directions in research. It's rather unique in the world in the sense that it brings together both theory and experiment and across multiple subdisciplines, including particle and nuclear physics, astrophysics, and quantum physics. And since the founding, we already have developed a large number of people, over 100 faculty, and it's quite international, as you see in the box there. So you can read more about it at the website there. I'm in the particle and nuclear physics division, and we have quite an interesting mix of faculty. You'll see our photos there. And again, a mix of experimental and theoretical research. And I encourage you to ask me about that later on or to read more about it on the website. And just for balance sake, I should also say something about the ACFI at UMass. This was founded a little earlier. It's a small but unique university-based research center that brings together physics at the three frontiers, which I'm talking about today, and has had a rather successful and ongoing program of targeted topical workshops. And again, you can read more about that at the website listed there. So science first, and there we go. So let me say what the goals are for this talk. What I first want to do is motivate for you, those of you who have not been thinking about the thermal history of electroweak symmetry breaking, motivate for you the scientific opportunity associated with a possible early electroweak phase transition that would occur in BSM scenarios. I'd like to introduce the ideas of effective field theory that are used in studying the thermal history of electroweak symmetry breaking, illustrate the interplay with non-perturbative computations, and highlight some of the recent results from my collaborators and myself that draw on this interplay. And so here are some of the key ideas. The first is to note that there is a scale in nature that makes this a very interesting question for both theory and experiment. It's called the electroweak temperature, and it gives us a very clear beyond the standard model target for experiments in the next generation, both collider and, as we'll see, gravity wave probes. There also are very simple arguments that any BSM physics that might change the thermal history of electroweak symmetry breaking from what you get in the standard model can't be arbitrarily heavy or too feebly coupled to the standard model in order for this effect to happen. So that also makes this quite an interesting target for experiment. But to really nail this down, we need to make a robust test of theory, we really have to vigorously pursue a program of EFT and non-perturbative computations, which I'm going to be talking about in the latter part of the talk. And so some new results I want to use to highlight this, what I call theoretical frontier. So the key ideas are going to draw on these sets of papers, which I've listed here, so I won't belabor the names here because I'll come back to them. And I do want to apologize for anyone who's listening, who's worked on these topics. In the rush to complete this talk before this morning, I didn't get a chance to put in all the references I might have liked, so I apologize if your work has been left out. But I do want to mention that the vital role of all my collaborators, all of whom are much earlier in their career than me, and several of them are involved in the program in Shanghai. So here's the outline. I'm going to give you some of the big picture context and questions, and then make a few remarks about why the electroweak phase transition is a very interesting experimental target, and then focus mostly on this issue of what I call theoretical robustness and the role of effective field theory in a very brief outlook. So the context and questions. Why is the possibility of an electroweak phase transition interesting? And the answer for me is really 3 bullet points. The first is, with the discovery of the Higgs, just the sort of conceptual question now really front and center is, what was the thermal history of electroweak symmetry breaking? The second and third bullets are maybe more familiar to people. If there was a first order phase transition during electroweak symmetry breaking, that could have created the conditions for electroweak baryogenesis and the possibility of producing gravitational radiation at a level that might be observed in LISA and other future gravity wave experiments. So let me say a little bit more about this first bullet. And I want to do so by making an analogy with what's been a huge topic of study in quantum chromodynamics, the thermal history of the confinement-deconfinement transition and the relationship to chiral symmetry breaking or restoration. Here, just to illustrate, is the QCD phase diagram. On the vertical axis is the temperature. On the horizontal axis is the baryon chemical potential. And I don't know if you can see my cursor here, but there is a line that marks the location of a first order phase transition. So that if the universe would have cooled down at sufficiently high baryon chemical potential, there would have been a first order phase transition. It ends somewhere at rather small baryon chemical potential. And what we've now learned from a combination of theory and the Rick experiments is that the standard model was a crossover transition. So that's been an object of immense study. And so now we can ask the same question about the electroweak sector of the standard model. And for most people, the starting point is the effective potential. Here is a cartoon of the effective potential as a function of the Higgs VEV. The vertical axis is the free energy or the potential. The horizontal axis is the Higgs VEV. And what's illustrated here are 2 possible thermal histories. On the left is a first order thermal history, first order phase transition history, where as the universe cools, secondary minimum develops away from the origin. And at some temperature below the critical temperature, when the origin and the broken minimum are degenerate in energy, the universe makes a transition to the broken phase. As one turns up the Higgs mass, this first order transition gets weaker and weaker. At some point, it becomes a second order transition and then ultimately a crossover transition. And what we now know, and actually have known for some time, is that for 125 GeV Higgs, the transition was a crossover. So we know this with good confidence from non-perturbative studies, lattice studies. On the bottom left of this slide is a compilation of some of the work that was done quite some time ago that identified the maximum Higgs mass or the critical mass for a first order transition in the standard model. And it's somewhere in the 70 to 80 GeV range. And so if we would turn this information into a phase diagram, what I would call the electroweak phase diagram, this is on the upper right of the slide. Here one has now on the vertical axis the temperature again, the horizontal axis is the Higgs mass. I put sort of schematically the line for a first order electroweak phase transition, and it ends around 70 to 80 GeV. And of course, 125 GeV Higgs is well above that. So in the standard model on the universe, we're quite sure that the transition of electroweak symmetry breaking was also a crossover transition. Now, for a lot of people like myself, we don't think the standard model is the end of the story, that there's some physics beyond the standard model. And so the question is, if that physics lives at the TeV scale and below, how does that change this phase diagram? And in particular, could there be a SFO EWPT, which is strong first order electroweak phase transition? And I'll explain the strong part in a minute. So how does this picture change is what we're interested in. So in thinking about this, I've been quite captivated by some ideas of Steve Weinberg that he put in his 1974 beautiful paper on gauge theories at finite temperature. And he pointed out that once one extends the scalar sector, there's a rather rich landscape of symmetry breaking patterns in the early universe. Here's an illustration from an example from his paper. It's not the standard model, but it's a theory with an ON cross ON group structure. And there are two Higgses in the theory, phi1 and phi2. Their masses are shown on the axes here. And these lines with labels 1, 2, 3, 4, 5, etc., identify different possible trajectories of symmetry breaking depending on the values of the Higgs masses. So line number 1, for example, is kind of the conventional idea of start in the most symmetric phase, and as the universe cools, now follow the cursor, you end up in a phase with a somewhat lower symmetry, like in the standard model. On the other hand, you might have started at 0.3 in a lower symmetry phase, and then lower the temperature, the symmetry actually increases for a while, and then breaks again to another broken symmetry, et cetera, et cetera. So by a very simple sort of setup of the scalar sector, there's already a much richer landscape of symmetry breaking possibilities as a function of temperature than one would get in the sort of what I call the vanilla standard model Higgs doublet only sort of setup. So I've been thinking about what are the landscape of possible potentials and symmetry breaking patterns if you extend the standard model Higgs sector. And here's a very simple sort of illustration of how it might be. So now here's a picture, a schematic picture of an effective potential, now as a function of the Higgs VEV in one direction, and the VEV of some BSM scalar I call capital phi in another direction. And you can see that there are various minima and maxima. And at the end of the day, we have to live over here in the Higgs phase at our current temperatures. So the question is, how do we get there? So you might have started, like in the standard model, at high temperature in the symmetric phase and just directly break the symmetry to the Higgs phase. But another interesting possibility is the universe first goes to a different phase associated with the phi VEV, and then to the Higgs phase, a multiple step transition. So already by adding one field to the standard model, there's already a richer possibility of symmetry breaking patterns. And so I just think there's a very, we don't know what could have happened. And so this is really interesting to explore. So the questions one can ask are, what are the landscape, or what is rather the landscape of potentials and their thermal histories? And then how can experiment help us identify whether any of them is right? And more to the point of this talk, how can we compute the thermodynamics as well as the dynamics associated with these different possible patterns of symmetry breaking in the early universe? Now, the other two motivations for this topic are a little more familiar to people, as I said, baryogenesis and gravitational waves. For both, one requires a first order transition, which would proceed through the nucleation of bubbles of broken electroweak symmetry in the background of the symmetric phase. And that transition has to be relatively strong for successful baryogenesis at the weak scale, as well as to make observable gravitational radiation. And so these are targets for us to think about theoretically as well. So now on the topic of target, I want to say why one has some reasonable confidence that ultimately a combination of theory and experiment might be able to help us nail down this landscape of potentials. And there are two elements here for experiment, the mass scale and the precision. So let's think about experimental probes of these kinds of landscapes of potential. One clear probe is to make the new scalar directly in a collider experiment. So here's your BSM Higgs that you might look for. There's also the possibility that's quite relevant to the future Higgs factories that the presence of this extended Higgs sector in the potential would cause small changes in the properties of the standard model Higgs, what I call a kind of tickling of the standard model Higgs due to the presence of the new scalar and its interactions. So can one use both of these to maybe look for the potential and its interactions that might tell us that there was a first order phase transition in the early universe? And then, of course, the very convincing signal would be the actual direct observation of the gravitational radiation produced through the first order phase transition. So there's a very rich interplay here between collider physics and astrophysics. And as I said, I think there's a good argument for why the next generation experiments may be able to really conclusively probe this possibility. So to address that, the questions are, how heavy can the new scalar be? How does it couple to the Higgs, and can it be discovered in these experiments? Now, as I mentioned, the reason why there's some chance for doing this is that there's a scale in nature that's very important. It's called the Electroweak temperature. And to illustrate what that is, let's start with the leading order high temperature effective potential for the Higgs field in the standard model. That's shown in the red box here. And there are two important terms. There's the quadratic term and the quartic term. The quadratic term is a function of temperature T. And this quantity T naught squared I show in the second box is actually a prediction within the standard model. Here's what it looks like in perturbation theory. You can see that it's proportional to V squared. V is the Higgs VEV, but it's not identically equal to V. It depends on all the other important couplings in the theory, including the quartic Higgs self-interaction, the gauge couplings, and importantly, the top quark Yukawa coupling. And so when you put all the numbers together, T naught turns out to be about 140 GeV. So that's the temperature that characterizes electroweak symmetry breaking in the standard model. And that number is quite close to what one gets from lattice studies, actually. So that's our target, and that's why there's some chance that this physics is accessible to experiment. Now, to get a first order phase transition, which we don't have in the standard model, we need a barrier between the symmetric and broken phase. And so we can think about how the addition of an additional scalar might generate that barrier. So I'm going to illustrate that with a very simple Higgs portal sort of setup. And there are three kind of representative patterns of symmetry breaking that one might expect in this very generic but simple setup, associated with different interactions between the new scalar phi and the Higgs. And these are shown along the bottom of your slide here. Let's start over on the far left. The horizontal axis is the Higgs field, the vertical axis is the new field phi, and one possible trajectory for symmetry breaking is a direct transition to the Higgs VEV at the electroweak temperature. And this could become first order due to loop effects that arise from an interaction, a quartic cross interaction between the Higgs and phi with some coefficient I call A2. So this is a finite temperature effect. A second possibility is in the middle of this bottom part of your slide, where the universe would make a two-step transition that I talked about earlier, first going to a phi phase, and then from the phi phase to the Higgs phase. And there can be a barrier between the phi phase and the Higgs phase associated with the same quartic interaction, but that barrier already exists at zero temperature. And now it's a function of temperature, how you first go to the phi phase and then cross the barrier to the Higgs phase. And lastly, there's a possibility on the far right of going in one step to a commonly broken phase where there's a barrier that might be created by a cubic interaction with a coefficient I call A1. So one can show, and I don't have time in this talk to go through the arguments, that for these first two possibilities, that if there's going to be a first order phase transition associated with either of these trajectories, the mass of the new scalar can't be too heavy, maybe about 700 GeV, which is well within the range of collider sensitivities. For the third possibility, the very interesting new effect is the generation of mixing between the neutral component of the phi field and the Higgs. And that mixing can be accessible in precision tests. And one can again show that if the transition is first order and sufficiently strong for baryogenesis and observable gravity waves, that mixing angle can't be too small. And for example, that would lead to a lower bound on the shift in the Higgs quartic self interaction that might be accessible in future experiments. So with these sort of generic arguments in mind, there's lots of work that's been done on the model building and phenomenology related to a first order phase transition. And so in this talk, I'm not going to go into any of the details about that, but you can read about it in this paper that I wrote or the references that I give you there. So what I want to do now is turn to this question of theoretical robustness in the theory. And going on to all the models in phenomenology, a question you should ask is, how reliable is the theory that we do based on these very interesting model possibilities? So when we talk about reliability, there are several inputs that one draws upon from thermal quantum field theory. There's the thermodynamics and the dynamics. And for the thermodynamics, as I've already discussed, one of the starting point is really to identify the phase diagram and to ask, is there anywhere in that phase diagram a first order electroweak phase transition? And then if there is, a very important quantity that one can compute from the thermodynamics is the latent heat of the transition, which is quite decisive for gravitational waves. For the dynamics, there are rates that one needs to compute, the nucleation rate and the Electroweak's Phaleron rate. The nucleation rate is important because it tells us whether a transition, the thermodynamics tells us whether there could have been a first order transition. The nucleation rate tells us whether that transition actually occurred. If so, what is the nucleation temperature and how long did the transition last? And then for baryogenesis, there are Electroweak's Phalerons that have to get quenched in order to preserve the baryon asymmetry. And the question is, what is that rate as a function of the parameters of the theory? So how reliably can we compute these quantities that whether in a given BSM theory, there was an interesting first order phase transition? And I see there's a question in the chat. Yeah, by the way, the slides will be available. I can see that question. So, so let's talk about why you might worry. You should worry about theory, and in particular, most people in phenomenology and model building use perturbation theory, and perturbation theory is fraught. Let me just say that from the beginning, and let's illustrate that. This is fraught for a couple of reasons. One is the so-called IR problem or the Linda problem. Let's illustrate that with a bosonic loop that might appear at non-zero temperature. So that's given in this formula here. It's a three-dimensional momentum integral with some coupling squared, some propagators of the boson, and the Bose distribution function. And let's look at that Bose distribution function in the small momentum regime, the IR regime, where it basically goes like the temperature over the mass of the particles in the loop. And so in that regime, the integral has a form that's shown on the upper right, and the prefactor now is not just the gauge coupling squared, but the gauge coupling squared times temperature over the mass. So this is our effective expansion parameter. And it depends crucially on the mass in the denominator, which in the theories we're interested here is in general going to be field dependent. So for example, the Higgs mass or the gauge boson masses are generally functions of the background field phi and the gauge, the temperature T, that's the thermal mass. And so what happens is near a phase transition, phi is close to zero, at least starting, and the thermal mass can be much smaller than G times T. So this prefactor of the integral is not necessarily small. Even though G might be small, G also appears in the denominator. And so in general, one has a problem with convergence due to the IR physics of these bosonic loops. And so just to take an example from earlier studies by Mikko Laine and others, this effective expansion parameter I call G effective for various reasons, a pi is usually put in the denominator. That's not small, even in the standard model, in the vicinity of a first order transition for the maximal Higgs mass, 70 GeV. And so one really has to be careful about perturbation theory. There's a second problem that people may be a little more familiar with, which is that even within perturbation theory, there's a possible issue of the loop expansion not being good. It's not just a possible issue, it is an issue. And let's take an example of the thermal mass, again, of the Higgs, phi, which is given at one loop by the formula on the left of your slide here. And one can ask about higher loop corrections. Well, higher loop corrections will go like the original loop times some quantity I call zeta. And zeta is again a function of this temperature over the field dimension dependent mass. And as we already said, that's not necessarily small. And so more and more loops come with more powers of zeta, but they're not necessarily suppressed. And so this parameter, can be order 1 near the phase transition, as we already discussed. And so one needs to resum these loops. Now that's done in this complicated formula that I won't talk you through here. It's called the Daisy resummation. This hasn't been known for some time, but it's really an ad hoc addressing of a problem that people realized and not really systematic. And so what we're going to see is that in the use of effective field theory, this kind of thermal resummation and perturbation theory can be done much more systematically. So the challenges for theory. We have perturbation theory, which is fraught because of the IR problem. One has this issue of thermal resummations. Two other issues I won't be talking about today are maintaining gauge invariance, especially when the barrier is generated through radiative corrections, and renormalization group invariance at finite temperature. People who do BSM physics and phenomenology use perturbation theory encounter all of these problems maybe unconsciously. And so what are we going to do? Now, you'd like to do the studies non-perturbatively, where the infrared problem in particular is done on the lattice, but that's computationally and labor intensive. And so here's our real conundrum. We'd like to use non-perturbative methods to really assess the robustness of a possible first order phase transition, but it's not practical to do a broad survey of scenarios in parameter space with these methods. On the other hand, perturbation theory is what we got to start with to do a broad survey of models and parameter space and connect with experiment, but the quantitative reliability at best needs to be verified. So the strategy that I've been pursuing and my collaborators have been pursuing is to benchmark perturbation theory through the use of non-perturbative methods. And in this context, a key element is the use of effective field theory to connect perturbation theory and the non-perturbative computations. So in the rest of the talk, I'm going to spend some time introducing for you the use of effective field theory that comes into this program. Hopefully now you have some better motivation for why it's important. In fact, it's crucial. So the strategy is we're going to employ something called the dimensionally reduced three-dimensional effective field theory in two regimes. One regime is where the BSM physics is quite heavy, and so you can integrate it out, and it turns out what we say is repurpose existing lattice computations. But that physics might not be so heavy, in which case we need to perform new lattice computations. And so you'll see some results for that. And in either case, we're going to try to compare the perturbative computations where the state of the art really is done using effective field theory with the non-perturbative computations at benchmark parameter points in selected models. So now, effective field theory. There actually are several effective field theories that one encounters in this business. One is relevant for purely the thermodynamics. And for purposes of this talk, I'm going to call it EFT1. When we come to dynamics, there's at least one or more new scales in the problem. So that calls for different effective field theories. The one for nucleation, I call EFT2. And for sphalerons, I'll call it EFT3. And just so you're aware that EFT3 is not fully developed yet. It's under construction, but that's something that we are working on. So what is this general dimensional reduction EFT really about? So to introduce it, let's start with the scales that are relevant for these problems. And they're listed here on this slide. At the top is pi times temperature. This is the scale associated with what are called the non-zero Matsubara modes in thermal field theory. And if you're not familiar with Matsubara modes, I think I have a backup slide. If there's question time at the end, I can talk you through that. There's the scale of the BSM physics, M, that can be either larger or smaller than pi times T, the Matsubara or the heavy, super heavy, we call it the super heavy scale. There's the scale of thermal masses, G times T, and you've already seen that example earlier. In the case of nucleation, there's the scale associated with the inverse size of the bubbles. We call that the nucleation scale. And then there are smaller corrections to the potential quadratic term called, and we call it the light scale, that go like G squared times T. So EFT1 organizes the problem according to the scales in the green boxes here. And that's what I'll be focusing on in the rest of the talk. EFT2 includes the same scales plus the nucleation scale. And I'll give you some references where you can read about that. So here's the way the EFT organizing of the scales work. So we start in this diagram. So these scales are organized along the vertical axis, and we start with the pi t, which we call the super heavy scale. And the full theory, lives at that scale. And the first step in deriving the EFT is to integrate out the non-zero Matsubara modes, whose mass scale is set by pi times temperature. And we end up with an effective field theory with a Lagrangian L3. It's a three-dimensional effective field theory, and I'll explain that in just a minute. Then it is possible to integrate out fields that have what we call the heavy scale masses, the thermal masses G times T. That would include, for example, the time component of the gauge fields. And we end up with another effective field theory. This is all EFT1, by the way, with the Lagrangian L bar 3 that retains the zero Matsubara modes and the mass scales in this particular problem. The thermal mass scales are now light, G squared times T. So why is the theory three-dimensional? That's dimensional reduction. And let's start with the key point, which is shown on the left in here. It's a four-dimensional integral in zero temperature. At finite temperature, for various reasons, becomes a three-dimensional momentum integral, a sum over all the Matsubara modes, that's the sum on n, and the prefactor of temperature, beta is 1 over temperature. So there's temperature times the sum times the integral. This is called a sum integral. And so now the theory is three-dimensional, and so it's convenient to redefine the fields for dimensional reasons in the 3D theory. And so the rescaling of the fields and the couplings at this level is given when the bullet's on the right. So there are factors of T that come into the rescaled fields and couplings. Now you can ask, what about the loop effects? So the loop effects are computed in integrating out the non-zero Matsubara modes in the first step, and to make sure that the effective field theory reproduces faithfully the physics of the full theory, we of course equate Green's functions, and that leads to additional corrections to the fields in the 3D theory and the couplings in the 3D theory. For example, on the lower left here is the formula for the three-dimensional Higgs field. It's got a 1 over T times, its square has a 1 over T times the four-dimensional field. And then there's an additional loop correction involving the derivative of the self-energy function, pi. For a coupling, for example, this quartic cross-coupling that I introduced earlier called A2, in the 3D theory is proportional to temperature times the 4D coupling. And then there are additional corrections involving the pi functions for the fields. In this case, there's another field called sigma. I'll come to that a little later on. And then there's a vertex correction called pi hat. And so this is how the loop functions are encoded, the loop effects are encoded to maintain the physics coming from the heavy scale in the effective field theory. So here we go. Now, I also want to mention that I said the effective field theory systematically does this resummation that has been done in a sort of ad hoc way in the past. And that is, in this first step, done through these loop effects by integrating out the non-zero Matsubara modes. When we come down to the super light theory, in some cases, when everything is heavy except the remaining standard model degrees of freedom, we have a potential that looks like the standard model potential, but the couplings are not quite the same. And in particular, when the full theory contains beyond the standard model interactions, the values of mu3 and lambda3 can accommodate a first order electroweak phase transition, even if the standard model Higgs is 125 GeV. If we didn't have those BSM effects that come through the integrating out, then mu3 and lambda3 would not be able to give a first order phase transition and 125 GeV for Higgs. So that's really the way to think about the impact of the new physics in this EFT sort of context. So one of the things we can do then is, as we say, repurpose existing standard model like theory lattice calculations that were based on this formula V bar, V is a function of mu bar and lambda bar, and identified the regions in the parameter space for these quantities that would give a first order phase transition, and then ask, what would the values of the full theory parameters have to be such that mu bar and lambda 3 bar end up in the first order phase transition region of parameter space. So here's the program. We assume to start the BSM fields are heavy or super heavy, and we integrate them out. So that's this first step or two steps. We end up with the effective standard model like theory that's a function of whose parameters are functions of the BSM parameters in the full theory. And then we're going to use the existing lattice calculations to look for where those full theory parameters would have to be to land you in the right region of lambda bar and mu bar space. Let me illustrate what we learn in this program with one model, which is to add to the standard model the simplest thing you can add with gauge interactions. It's a real triplet, a real scalar triplet. And this real scalar triplet is a QCD singlet. It's a hypercharged singlet, and it exemplifies what I talked about earlier, is the possibility of multiple step phase transitions that are first order through combinations of loops and a tree level barrier. So one can have a single step transition to the Higgs phase, like I talked about earlier, or one can have a two-step transition. And in that two-step history, electroweak symmetry is broken twice. First in step 1, when we go to the sigma phase, and step 2 to the Higgs phase. And so back to this picture I showed you earlier, the potential and the possible symmetry breaking trajectories look like the arrows that I show you on the lower right. So this is very interesting because one can actually have electroweak baryogenesis take place in the first step, make the baryon asymmetry in the sigma phase. We call it phi here in this slide. Didn't update the slide, sorry about that. And then that baryon asymmetry can simply be handed to the Higgs phase in the second transition, for example. So let's now illustrate how the presence of the triplet could lead to a first order transition in the one-step trajectory that I introduced earlier. And I want to do that by first illustrating from the standpoint of effective field theory how that in principle could work. So here's the potential for this particular model. We've got the mass terms, the Higgs mass term and the triplet mass term, and then we've got the quartic interactions for the Higgs and for the triplet, and then we've got this cross-quartic interaction here, phi squared, sigma squared. And now we can ask, what's the effect of these interactions on the lambda parameter when we integrate out the non-zero Matsubara modes associated with the triplet? And that's shown in this formula in the second red box that comes from matching to the heavy scale. So here's lambda 3. It's a proportion of the temperature, as I mentioned earlier. And then there's a contribution from the cross-quartic interaction. And because of the sign at which it comes in, this term, this effect can make lambda 3 small enough to give a first order phase transition, even though at zero temperature, the Higgs mass that depends crucially on lambda, lambda of capital lambda, is consistent with 125 GeV. So here's how we see that in pictures. Now using this combination of effective field theory to map out the parameter space and lattice computations, as I said, that are repurposed. So in this plot, on the horizontal axis is the triplet mass, and on the vertical axis is the Higgs portal cross coupling, A2. The colors correspond to different types of transitions, to one-step transitions to the Higgs phase. The gray region I'll come back to shortly. The blue region is where there would be a crossover transition. And the green regions are where there would be a first order electroweak phase transition. And the first thing I want to emphasize is that it is not possible to identify the boundary between the crossover and first order phase transition regions solely using perturbation theory, because this is very sensitive to that IR problem, as I mentioned. And again, we'll see in a few slides, again, even with effective field theory, you can't do that. But one can still sort of map out where the first order transition is and where it gets weaker and weaker using effective field theory, and then match it onto the lattice computations and work backwards to this parameter space. Okay, so now there's interesting phenomenology that one can do with this phase diagram. This is the phase diagram that I said might be changed. These dashed lines correspond to the effect of the triplet on Higgs diphoton decays. Since the charge components enter through loops to the Higgs decay, their sensitivity to the Higgs portal coupling and the mass from the of the Higgs diphoton decay rate to the Higgs portal coupling and the mass, and one can map out lines of constant shift, relative shift in the Higgs decay rate due to this effect. Map it out in this parameter space. So delta corresponds to the relative change in the Higgs diphoton decay rate. For this region of parameter space, it's always negative. And so you can see that if we measure at a Higgs factory or the LHC high luminosity or even beyond, the Higgs diphoton decay rate and find that it's, say, 8% smaller than standard model, you would end up on this dashed line that my cursor is moving over here. Now, you might also want to know something about the mass. And for this particular model setup, a very interesting way to look for the mass of the triplet is to search for disappearing charge tracks. So you might learn from disappearing charge tracks that say the mass is 280 GeV or 500 GeV. And the combination of that information and the Higgs diphoton decay rate then might tell you whether in this particular setup, you're in the first order phase transition region of the phase diagram or in the crossover region. So I think it's a very interesting combination of theory, effective field theory and lattice, and collider phenomenology. Now, I probably don't have time to talk about the caveats, which has to do with higher dimensional operators that arise when you develop the effective field theory. And so I'll leave this for question time in case anyone's interested. Now, the last thing I want to talk about is what happens if the triplet, which in that previous set of slides was heavy enough to be integrated out completely, and we have just the standard model degrees of freedom, zero Matsubarra modes at the end. But what if the triplet is not so heavy and we don't necessarily want to integrate it out, but we want to include it as a dynamical degree of freedom? Well, in the first step of EFT1, there's still the matching effect, which I talked about. And so even in that case, as one should expect, there can still be a single step first order phase transition due to this effect on the Higgs cortex self-coupling due to the non-zero Matsubarra mode loops arising from the triplet. But we can go down now to the light theory and include the zero Matsubarra modes of the triplet as a dynamical degree of freedom, and then map out the same parameter space with EFT and test it using the lattice. And that's the last thing that I want to do, talk about here. And in particular, there's now this interesting possibility of having a two-step electroweak symmetry breaking history. And because the triplet is now going to be dynamical in the light theory, we can see where in the parameter space one might go in this second box here, first to the Higgs, the triplet phase, and then to the Higgs phase. So here's what the phase diagram looks like in that case. The colors are different, but the setup is sort of the same. So now the pink region is the crossover region. The dark blue region is a region where the electroweak minimum is unstable, so we don't want to live there. The red region is where the transition from the symmetric phase is one step to the Higgs phase and is first order. And this light, small region here of orange, gray, and blue is where there would be a two-step thermal history. And so that's the region that we recently really scrutinized with lattice computations. And as I said, you can't do it at every point in parameter space, so you have to carefully choose benchmark parameter points. And those are the crosses, the dark crosses, that we then scrutinized using the lattice to try to determine what is the nature of the transition in this case. So for example, what we learn from those studies is that in the orange region, the first step where we go to the triplet phase is actually a crossover transition. And then the second step where we go to the Higgs phase is a first order transition. In the blue region, both transitions are first order. And in the gray region, we didn't have enough information to really determine. It's a little bit, probably need more simulations to understand that. So we didn't make a definitive statement there. But again, the nature of the transition being crossover versus first order is not something we could do with perturbation theory alone. It is something that really requires the lattice simulations. Okay, so again, illustrating this marriage of lattice and EFT. I'll save this for question time. It's how we determine whether it's crossover versus a second order transition. We use something called the susceptibility. But I do want to sort of end with this slide here. Well, it won't be end, there'll be a couple more, that illustrates, even in the use of effective field theory, the possible breakdown of perturbation theory as a guide to a first order transition. So these plots here are done using two different benchmark points that we studied on the lattice. And let's go over on the right to start. On the horizontal axis is the temperature. On the vertical axis is the condensate scaled to temperature. The condensate means phi dagger phi, or sigma squared divided by temperature. The colors are blue is for the triplet, red is for the Higgs doublet, and the solid lines are two-loop perturbation theory using the effective field theory, and the dots are the results of lattice simulations. So, for example, if one looks at the right, we start at high temperature. Both the dots, the red and the blue dots from the lattice, tell us that there's no condensate. And then at about 123 GeV, the triplet jumps up in a discontinuous way to a non-zero value. So that would be indicative of a first order transition. And then as we go down in temperature, the triplet drops down to essentially 0, and the doublet jumps up rather in a discontinuous way. So this is 2 successive first-order transitions in that slice of parameter space I illustrated earlier. The solid are what you would get computing the same quantities in the effective field theory, and you see that we have 2 discontinuous jumps. The spike is something I can talk about later. And so the thing to note is that the temperature at which these jumps occur is not well reproduced by even our state-of-the-art perturbation theory. Okay, so there's caveat number 1. Now let's look over on the left. So on the left, in the blue, we see that there is a non-zero condensate that arises, but it's a smooth rise. It's a crossover transition. Whereas in the solid blue curve from perturbation theory, it still looks like a first-order transition. So perturbation theory can give you a misleading sort of indication of what the nature of the transition is. And so we really, in the end of the day, need the lattice. So this is one of the big sort of takeaway messages here, is that to say anything reasonable in perturbation theory, we need to do this EFT, but even there, that's not enough. We really need the lattice, okay? So, and I know there was a hand raised, and because I need to jump and catch my plane in a couple minutes here, let me just quickly say something about the connections with gravity waves using a different model where we add a gauge singlet. And here, for people who are familiar, the important quantities for gravity waves are the latent heat of the transition and the duration of the transition, which is on the vertical axis, characterized by a quantity called beta over h star. And in this parameter space here, one can work out where the signal to noise sensitivities are for, say, LISA. That's given at the lower right. Sort of maybe the best sensitivity you could get is sort of 5 signal to noise, and the more you go to the lower right, the stronger the signal to noise would be. It turns out that if we're in the 3D standard model like effective field theory, for example, no new light beyond the standard model degree of freedom, you would live in this purple region here, which is well away from the LISA or other next generation gravity wave sensitivities. So the moral of the story is that in order to have a potentially observable gravitational wave signal, we really need the BSM scalars to be sufficiently light to move us down toward LISA signal to noise, or there would be potentially some higher dimensional operators that one would need to include in the theory. So there's some other issues that I don't have time to talk about, but I really want to highlight recent developments in the theory that all rely on this effective field theory sort of setup here. And I encourage you, if you have interest and time, to take a look at some of these papers. And so let me go to my Outlook, and then we'll have about 5 minutes for questions. So then I know Venus has a question, so we'll be able to go back there. So takeaway messages are, first, big picture, determining the thermal history of electroweak symmetry breaking is really interesting in its own right, as well as having what I call practical importance for baryogenesis and gravity waves. There's this scale in nature, the electroweak temperature, that tells us we have a target for experiment, and that any new physics that modifies things from the standard model crossover history to a first order history has to live at masses below a TeV and couple with sufficient strength to yield in principle observable shifts in the Higgs properties. And so there's some chance that next generation experiment might actually really be able to probe this landscape of possibilities. And somehow I misordered my slides. Here's not backup slides yet. The key point is that to really make statements robustly, we need this new generation of theory using EFT and non-perturbative methods. And so there's lots of room for people in the EFT community to get involved. And so I encourage anyone who's interested to do so. And now I will end my talk. We have some time still for questions. Thanks very much.